Hi, this is Yash. I'll be presenting our work, HistoTransfer, Understanding Transfer Learning for Histopathology, done in collaboration with Lubena Hassan, Dr. Sana Syed, and Dr. Donald Brown. I'll quickly walk you through what is unique about whole slide image analysis in comparison to general image analysis, a bit of literature overview, our proposed architectures and questions that we explored as part of the study. We explored how much selection of pre-trained network impact the performance. We check if encoder model pre-trained on domain-specific data perform better than Imagenet encoder. In our prior work, we have observed fine-tuning base encoder lead to gain in performance. We explore if fine-tuning base encoder can recover the lack of specificity of encoder. We check if model can be truncated without affecting the performance. We extract intermediate block representation from DenseNet 18 and DenseNet 121 and use it with our transfer learning architecture for the classification task. Here we can see two examples, one from Imagenet and other from WSI dataset. An average Imagenet size is 500 cross 400 pixels, whereas a WSI can range from 50k cross 50k pixels to 100k cross 100k pixels, rendering traditional approaches unusable. Downsampling images lead to loss of relevant cellular and structural details pertinent for diagnosis. Further, there is variability in histopathological features across diseases, and we usually get limited data for training. So for tackling this problem, small patches are extracted from a WSI dataset of comparable size to Imagenet and are used for training deep learning model. Depending on the disease, proportion of patches containing disease can vary from 5% to 90%, and getting pixel level annotation for training model is an extensive task for medical experts. So we are not sure which patch in a WSI contains disease and which patch doesn't. So for addressing this problem, authors use multi-instance learning framework in which they assume at least one of the patches in a bag of unhealthy patient is unhealthy and all the patches in a bag of healthy patients are healthy. Using this framework, authors divide training in two parts. First part consists of training a CNN for generating representation of the patches or prediction for patches. Second part consists of aggregating these patch level representation prediction to WSI level prediction. Quickly before moving to our experiment design and takeaways, here we highlight some of the notable references that inspired our work. We divide these reviews into three categories: histopathology training framework, transfer learning, histopathology pre-trained encoder. In histopathology training framework, oftentimes to train first stage of previously explained model, due to lack of patch level annotation, the assumptions are made like all the patches coming from unhealthy patient are contain disease. These assumptions are not always right and have increased the interest in end-to-end training using WSI, in which both patch feature generation module and aggregation module is trained together in synergy, going away from all the previous assumptions. And it has been observed that these architectures lead to superior performance. C2C by Sharma et al., beyond classification by Z et al. Are some of the examples. In contrast, recently Lu et al. Proposed a weakly supervised attention-based learning approach CLAM, which used a pre-trained encoder to extract all patches representation followed by attention pooling for WSI classification. They showed patch representation generated by Imagenet leads to competitive performance. There is an active interesting amount of work being done in exploring transfer learning in general and specifically in medical images. Key et al. In their work Chest Transfer demonstrated that there exists no correlation between the Imagenet performance and chest X-ray performance, concluding that improvements observed on Imagenet may not be directly transferable to medical imaging tasks. Further, they demonstrated the final blocks of pre-trained model could be truncated without observing a significant drop in performance. Rago et al. In their work Transfusion demonstrated smaller models perform comparably to bigger models, and Imagenet performance is not indicative of medical performance. Further, using representation similarity metric, they showed that representation of Imagenet models do not change significantly through the fine-tuning process. Recent availability of multiple small size and medium size histopathology dataset has made the development of domain-specific pre-trained encoder using different strategies possible. Seeger et al. Used a contrastive self-supervised learning method for training on 60 histopathology dataset images to develop a domain-specific encoder, demonstrating that linear classifier trained on top of their encoder features perform better than Imagenet pre-trained network. We use their publicly released weights of pre-trained DenseNet 18 for our experiment. Bobment et al. Use multitask learning as a way of pre-training models for developing histopathology specific classification model. They use data from over 22 publicly available histopathology classification tasks for training. They reach similar conclusion that domain-specific pre-trained encoder benefit max in feature extraction tasks. However, fine-tuning can recover the lack of specificity of the Imagenet pre-trained encoder and give comparable performance to domain-specific encoder. We use their publicly released weights of ResNet 50 and DesNet 121 for comparison. In our transfer learning experiment, we used different pre-trained encoder with attention pooling aggregation model for experimentation. In our fine-tuning experiment, we extend the transfer learning architecture and use top 64 disease probable patches for training base encoder in synergy with aggregation module. In our transfer learning architecture, we investigated if the performance gains observed with ResNet, DenseNet, and EfficientNet architecture on Imagenet are transferable to histopathology data. We observed that there is no significant relationship between histopathology AOC and Imagenet top 1 accuracy. We observed that within each architecture family, smaller architecture achieves similar if not better performance compared to bigger architectures, as can be seen in the table. We conclude that increasing complexity within the model does not yield in an increase in histopathology performance. On average, ResNet and DesNet family of algorithms perform better than EfficientNet. This corroborates the observation made in the prior work HistoTransfer that recently released algorithms are generated through neural architecture search, optimizing performance on ImageNet. But such performance gains may not be directly transferable to medical image dataset. For evaluating encoder trained on histopathology, we only used the gastrointestinal dataset, as the chameleon dataset was part of the training set in both the references. We observed that encoders trained using both self-supervised learning and multitask learning on histopathology data lead to superior performance, resulting in higher AOC in our transfer learning architecture. This satisfies the observation from Moment et al. That domain-specific encoder performs better for feature extraction than Imagenet encoder. And we suggest that these publicly available weights should be used for weight initialization in histopathology-specific tasks. Further, to check if by fine-tuning the Imagenet encoder we can recover the lack of specificity of Imagenet encoders, we fine-tune DesNet 120 and DesNet 18, initialized using Imagenet. Using top 64 patches and a small learning rate, we fine-tuned our model. We significantly improved the AOC on the chameleon dataset while achieving minor improvement in the gastrointestinal dataset. For the gastro dataset, we could not recover the differences observed between Imagenet initialization and multitask learning initialization. We hypothesize this is happening because domain-specific encoders are superior for histopathologic classification tasks, and we require either pass-level annotation or a larger dataset for recovering these differences. Further, using similarity metric, we study the block-wise representation of encoder to understand the fine-tuning step. Both ResNet 18 and DesNet 121 consist of 4 blocks. We extract representation at each of these blocks and compute similarity between frozen encoder representation and fine-tuned encoder representation. We observe that relatively maximum change in the representation is happening in the later blocks, aligning with the understanding that initial layers of deep architectures learn more general representation, and as we move towards the penultimate layer, more task-specific patterns are learned. Motivated by these findings and conclusion from HistoTransfer highlighting that bigger models can be pruned without significantly impacting the performance, we examined if blocks of deeper architectures can be truncated without affecting the performance. We pruned blocks of ResNet 18 and DesNet 121, reported the performance using transfer learning architecture. We found that removing the final block in both the models does not impact our performance, and there is a small drop when we remove block 3. This aligns with our observation from similarity analysis that later blocks in the deep models learn domain-specific features and can be pruned without significantly impacting the performance of the feature extraction step, resulting in parameter-efficient and higher resolution cams for interpretability. In this paper, we conclude that gains observed in the Imagenet dataset using bigger model are not transferable to histopathology dataset. Smaller models like ResNet 18 and DesNet 121 tend to perform better than larger counterparts. We demonstrated that domain-specific encoder trained on multiple histopathology datasets result in superior performance for classification tasks than their Imagenet trained counterparts, and should be used for weight and initialization in histopathology tasks. The performance can be further improved by fine-tuning the base encoder on top attended patches. Using representation similarity, we systematically studied the representation similarity between frozen and fine-tuned encoder and performed block pruning, concluding that later blocks of our encoders can be removed for feature extraction without impacting the performance of the model, leading to parameter-efficient models and higher resolution cams. Thank you for listening to our talk. Our code is open source. Feel free to reach out for any questions.